Hi there and welcome to this video series for Integrated Math 2. This is Lesson 1 in Unit 2. As always, let's start with our warm-up for today. So if you would try these 5 problems and see what you can do on those. Keep in mind that you can try to do mental math as we go. Okay, so let's go ahead and look at number 1 here. So if we solve this equation, there's a number of ways to do this. Probably the best way is to subtract 7 on both sides. When we do that, we get 6x equals 25 minus 7 is 18. And then if we divide both sides by 6, we can actually solve for x. So we're going to divide 6x by 6 and get x. 18 divided by 6 is 3. So 3 satisfies that equation. Number 2, function type. So what function type is this? In our first unit, we talked about a lot of different function types. In this case, the V shape is what we call absolute value function. So hopefully you remember that from the last unit. So this is an absolute value. Number 3, 4 to the negative 2 power. We talked about a lot of different exponents in our first unit. We talked about positive integer exponents, we talked about 0, and then we ended up talking about negative. Let's revisit that real quick. So if we have 4 squared, that's 16. 4 to the first is 4. And the pattern that we saw last unit was this right side is just dividing by 4 each time. So we said that 4 to the 0 would just be 4 divided by 4 is 1. 4 to the negative first power is 1 divided by 4 again is 1/4. Therefore, 4 to the negative 2 power, continue dividing by 4 one more time, and you get 1/16. And so 4 to the negative 2 power is 1/16. The other way you can think about this is it's the reciprocal, so the negative part is the reciprocal of 4 to the positive 2 power. 4 to the positive 2 is 16. The negative is the reciprocal of that, so 1/16, and you can get the same answer that way. So either way you want to think about it is fine, but I always like to go back to this pattern just to kind of remember why things are the way they are. Number 4, what's the next term here? If you noticed, hopefully, back in Integrated 1 you talked about arithmetic sequences, and this is an addition of 12 each time here. So if we think about the next term here, 41 plus 12 would be 53. Number 5, last one here, f of x equals this quadratic, x squared plus x minus 1. What is f of negative 4? We haven't talked a whole lot about quadratics yet, but I think you should at least be able to substitute values in. It's a very common question on the ACT. So let's substitute negative 4 in for our x's here. Don't forget your parentheses. When we put in values here, I always want to put them in parentheses. So we have negative 4 squared. So you square, that's just the number times itself. So negative 4 times negative 4 is a positive 16. Minus 4 minus 1. So 16 minus 5 is what we end up getting here. 16 minus 5 is 11. So hopefully you were able to get those 5 there. So at this time, we'll kind of transition into our lesson for today. Before I do that though, I do want to tell you that I do have students in the room with me today. So I will ask questions as we go to them. You'll hear them speaking and providing their ideas. So just know that up front. All right, so our goal for today is to understand how to multiply 2 functions graphically and identify key features of quadratic functions and describe the domain of a function in context. So in our first unit, we talked about a bunch of different function types. One of those function types was a quadratic function. That's going to be our focus of this whole entire unit in Unit 2. So these are our goals for today, and we're going to get into the first one right now. So when we think about multiplying graphically, I know that sounds weird because you're used to just multiplying numbers, multiplying expressions, those kinds of things. So you probably haven't thought about how to multiply graphically. So that's what we're going to start with today. So I'm going to pull up this little interactive here and let's see what we can do. So what we're going to do is we're going to multiply f of x and g of x. So those 2 linear functions. You remember those from Integrated Math 1, linear functions? So f of x and g of x are what we're multiplying, and the result of this multiplication is what we call h of x. So we have 3 functions involved here. F times g equals h. So one way to actually graph h of x So this new function that we're going to get by multiplying these two functions together, one way to do that is to simply multiply the y values of f and g at multiple x values. So let's try this below and see if we can make sense of this. So I've picked some x values to work with. So I've picked -4, -2. I've just randomly picked these. These are not special in any way. But at -4, so at -1, 2, 3, 4, we're going to multiply the two y values of f and g. And we don't actually know what f and g are yet. Like, we don't know what functions they are. We just know that they're linear. You might be able to figure out what they are by looking at the graph. But we do know what their y values are at this x value. So at -4, the y value for this red line is -2. So f of x is -2. Y'all with me there? And then the y value at -4 for g of x is down here at -7. So the y values for these two functions are -2 and -7 at this particular x value. So as we said a minute ago, our strategy here is to multiply the y values together. So -2 times -7 is what? 14, yes. So I'm going to type in 14 here. And when I type in 14, you can see some things happening in the graph here. So this visually shows us what's happening here. So we're multiplying -2 and -7, and it results in 14. So what we're going to do is we're going to do the same process that we did for -4. We're going to do it for a bunch of other x values. And by doing so, we're going to get a lot more values of h, like this green point here. We're going to get a lot more values of h that kind of tell us like what the shape of this new function is. Okay? So let's go back down to our next x value. -2 is our next x value. The y values of f and g are 0 and -5. What's 0 times -5? 0. Right? We're multiplying. Anything times 0 is 0, right? So we actually don't even see the red point here because the green one's on top of it. Does that make sense? 0 times -5 is still 0. All right, next one. At 0, we have 2 times -3. What's 2 times -3? -6. All right, 2 times -3 gives us -6. In this case, we're actually talking about the y-intercepts, aren't we? The y-intercept of f times the y-intercept of g equals the y-intercept of this new function we call h. All right, next one. We actually end up with the same thing, don't we? -6. All right. Now we have kind of a similar scenario as we had up here. Anytime one of them is 0, we're going to get what? 0, right? Because 0 times, it doesn't matter what this number is, right? You're still going to get a result of 0. And then lastly, at an x value of 5, we have y values of 7 and 2. 7 times 2 is 14. All right, so we've done this for quite a few x values now. Did we do it for all of them? No. I just picked some x values to do this with. But we can start to see maybe the overall shape of this new function that we're getting by multiplying these two functions together. So it starts up here, and as we go left to right, it looks like it might come down through here, and then something's going to happen here where I get from here to here somehow, but then it looks like it's going to come back up there. So any guesses maybe as to what the shape is going to look like overall? Maybe a letter in the alphabet, maybe? That it looks like? Any guesses? No? We're going to see, all right? We're going to see. So let's do this. Let's actually multiply them together to see what the actual function is for h of x. So we have x plus 2 times x minus 3. So if we multiply those together, I'm pretty sure you've done this before with the distributive property. All right, multiply something like this together where you multiply, you may have called it FOIL, but FOIL only works when you're multiplying a binomial, which is 2 terms, times a binomial, which is two terms. The problem is what happens when we multiply like a trinomial, which is 3 terms, times something. Then it doesn't work, right, at that point. But we can still do this. So x times x is x squared, right? X times x x times negative 3 is negative 3x. And then 2 times x is 2x. And then 2 times negative 3 is negative 6. So we get those 4 terms. And of course, the 2 middle terms are like terms. We can actually add those together. So x squared minus x minus 6. So let's go ahead and type that in so we can visually see what this looks like. So x squared minus x minus 6. And you can watch the graph as it goes through there. So if we had multiplied the y values for every x value, we would see this continuous function being formed instead of just a bunch of points, right? If we were to do it for every single x value, we would see this here. All right, what letter does it look like? A U, yeah. This is what we call a parabola. A parabola. It is the graph of a quadratic function. So if we scroll down here, this is a quadratic function because its highest power is 2, right? These highest powers, you don't see it, but it's actually an x to the first power, right? So those are linear functions. When we introduce a squared term, we have a quadratic function at that point, all right? So we've kind of seen how to multiply 2 functions graphically, but I want to pause. Any questions about that process so far? Like how we did that, why we did that, or how any of that works? Okay, so last thing I want to point out before we move on, I'm going to give you a chance to practice this, is just reiterating this. Anytime either one of these was 0, what did we get out? 0, right? We're going to really dive into that idea more so later in our next unit when we look at this more algebraically. But anytime one of these linear factors is 0, the quadratic is 0 at that point. All right? So let me give you a chance to try this. So multiply these 2 functions together graphically. And so we've got 2 linear functions, as you can see here. So let me give you a chance to do that. So pull out a sheet of paper and see if you can graph the result of multiplying these 2 functions together. Okay, so hopefully you were able to go through here and look at all the different x values and calculate what the new y value would be. So let's start with just from the left, and you can work your way to the right. You don't have to go in that direction, but it just makes sense to me. So at negative 3, what are our 2 y values there? Negative 2 and positive 5. Negative 2 times positive 5 is? Negative 10. So our new function, if we were to graph this, our new function would be down here at negative 10. All right? Negative 2, what are our 2 y values? Yeah, negative 1 and positive 4. So that multiplied together gives us? Negative 4 right here. All right? We shouldn't even have to think about this one, right? Because remember we said anytime either factor is 0, what's the new function? 0. So we shouldn't even need to think about this one. Our new function is going to go through that point right there. All right, at 0, 1 times 2 is 2. So I'm actually going to share that point with that line there. If we go on to 1, 1 times 2 again is 2. And then at 2 we have, we don't even need to think about that one, do we? Because again, anytime either of the factors is 0, our new quadratic is also going to be 0. All right, at 3 we have negative 1 and 4 makes negative 4 again, and then negative 2 and positive 5 makes negative 10. So we can kind of see that yes, it is going to be a little bit different orientation in that the one we saw before was concave up. Is what we call that, concavity in general. But concave up was the last example. This one's going to be concave down, meaning it's opening downward. I'm going to do my best to connect these dots here, but just bear with me here. It's actually going to peak in between these 2, and then work its way back down through there, like like that. Somewhat. So this is concave down, meaning it's opening downward. And as we're going to see in the next couple lessons, why this is. If we think about the two lines here, this one has a positive slope, the blue one here, has a positive slope of 1. So we have y equals, let's see, it's going to be x, and then the y-intercept is also 1. So this blue function is, maybe I should do this in blue instead, but the blue function is x plus 1. The red function is a negative slope, right? It's going down to the right, down 1 over 1, so it's going to be -1 slope, y-intercept of 2. So those are our two linear functions there. If we were to go ahead and multiply these together, so x plus 1 times -x plus 2, we would get x times -x is -x squared, x times 2 is 2x, 1 times -x is -x, and 1 times 2 is 2. So all in all we get, I'll put this in green because that's what we're talking about here, y equals -x squared plus x plus 2. So if you notice the difference between this quadratic and the last quadratic, let me remind you, so that's this one, and then this quadratic was positive x squared minus x minus 6. That's the key. This one's positive x squared, so it opens upwards. This one in our example here is a negative x squared, and that's the only thing that changes it from being open up to opening down, and that concavity that we've been talking about. So I don't want to get too far ahead of ourselves because this is more in the next unit, but I wanted you to go ahead and see why it's opening downward because of these linear factors. Okay, so we've seen how to multiply graphically. Now let's go ahead and get into identifying key features of graphs. In our last unit we talked about all these key features, but now we're going to specifically talk about the key features of quadratics. So let's take a moment and see if we can identify some of these key features. So I'll just kind of say a key feature and see if you can help me identify them. So what would the y-intercept be? 3? Yeah, and we'll actually go ahead and anytime we say y-intercept, we're talking about the whole point. So while it is at 3, the y-intercept is 0, comma 3. Yep, that's the y-intercept. All right, x-intercepts? Yeah, negative. Again, these are points here. -3, 0, and -1, 0. Okay, one other feature that we've talked about is the axis of symmetry. So the axis of symmetry is the line that if you were to fold over that line, it would land on itself. So what line would cut this in half essentially? -2. And in fact, it's more precisely x equals -2. So x equals is a vertical line, y equals a number is a horizontal line. So this is a vertical line that's going through the middle of this parabola that's cutting it in half. And it's called the axis of symmetry. So if I were to draw this, it would look something, it's not actually part of the function itself, but I can draw it just to kind of show you what that would look like. There. Another function that has an axis of symmetry is absolute value function. As we saw earlier, the V-looking graph, it's also symmetric across that middle there. Okay, so that's the axis of symmetry, is x equals -2. And then last one is the vertex. The vertex is, as we've talked before, maximums and minimums. So the vertex is either the maximum or the minimum value in a quadratic. So in this case, do we have a maximum or a minimum? Minimum, and it's right here. That is our vertex in this quadratic. So this is the point -2, comma -1. Now this is concave up, so as a result we have a minimum, right? But what if it was concave down? Would we have a minimum or maximum?
Yes.
Maximum. So that's kind of what changes when we change concavity. We go from having a minimum to actually having a maximum. So those are the key features of this quadratic. But I want to make sure that you know that this axis of symmetry means that any point we have on one side has a corresponding point on the other side. So from the vertex, I go over 1, 2, up 1, 2, 3, 4 to get to this point, right? So I should be able to do the same thing going to the left. Over 1, 2, up 1, 2, 3, 4. So I know this point as well is on our graph. So that's kind of how we can use the axis of symmetry. If we have one point on one side, we can actually find another one on the other side. Okay, so in this next graph, kind of similar scenario here, is this concave up or concave down? Concave down, so we do have a maximum. That's going to be one of our critical features here, or key features. It says the graph to the right represents the height of a swimmer as they jump off a diving board, with time being along the x-axis and the height of the swimmer along the y-axis. So the height of the jumper over time is what we're looking at here. So it says identify key features and describe what it means in the context. And then after that, we'll talk about what the domain is in this situation. So let me give you a couple minutes to identify the key features and describe what it means in the context. Okay, so let's go ahead and go through all the key features here. So let's start with the y-intercept. So the y-intercept, what would y'all say that is? What point? 0, 5, this point right here. 0, 5 is the y-intercept. Now what do you think that means in the context of this, the swimmer jumping off of this diving board? The height of the diving board, the starting point, right? The starting height of our jumper as they jump off the diving board. This is their starting height, right? So a lot of times the y-intercept represents the initial value. In this case, it's the initial height of the jump. Okay, then let's go to the axis of symmetry next. So what line? Don't give me a number, give me a line. What line represents the axis of symmetry here?
X equals 2.
Yeah, x equals 2, so this one right here. X equals 2. Okay, and then along those same lines, we have our vertex, which is the particular point on the axis of symmetry. And what would that be? Right here? Somebody said it. Yeah, 2, 9. Okay, so let's break this down, because as we said earlier, anything that's concave down is going to have a maximum at the top. But what does that maximum mean? So if we think about 2 and 9, what do you think that 2 represents? Okay, so it's the x value, right? It's the x value. What is x? What is your x-axis here? Time. So then it's 2 what? If we assume it's seconds, right? I don't think he's going to be in the air for 5 minutes, right? Let's assume it's seconds. So yes, after 2 seconds, he reaches a maximum height of 9, and we'll say it's in feet. I should have put that up there, but feet, right? So after 2 seconds, he reached a height of 9 feet. And then from there, he started to go down, right? And then what about our x-intercepts? What are those? What's one of them? -1, 0. Okay. -1, 0. And then the other one? 5, 0. Okay, so let's think about what those mean. Let's start with 5, 0. After 5 seconds, what happened? Hit the surface of the water if the surface of the water is 0 feet off the ground, right? So at 5 seconds, he hits the surface of the water, which is not all that realistic. I don't think you're going to be there for 5 seconds. That's a long time to be there. But just for this particular example, yes, that's what happened, right? He went up after 2 seconds, reached the maximum, and then after 5 seconds, came back down and hit the water. after 5 seconds. Now, let's go to this one. -1, 0. After -1 seconds? Like, what is that? What is that telling it? Like, does that mean anything? No, right? Like, we're saying that the jump starts here, right? At 0 seconds, right? If you watch a rocket launch, they count down. They say T minus 5, 4. Like the minus part is it's seconds before whatever it is that's happening, and then they say 0 and it launches, right? So it's the same thing here. The negative seconds don't mean anything, right? It's only at 0 to 5 seconds that actually is modeling what's the jump, right? Because think about 6 seconds. I mean, yes, we could say he's like, in the water or whatever. But if this was a ground, then it wouldn't be going in the ground, right? So you got to think about that too. Like if we're talking about water or ground or whatever, that makes sense. But definitely anything to the left of the y-axis here does not apply to the jump itself. So that gets at this last question here. What is the domain of the situation in the context of the problem? Okay, so let's assume we're only talking about the jump from the board to the water. That's all that matters. So what's the domain here? Remember, domain is all the inputs or x values that matter or can be inputted into our function. So what x values are we talking about then if we're going from the jump to where he hits the water? 0 to 5. That's the only thing that matters in this case, right? So in the context of the problem, the domain would be from 0 to 5. If you do interval notation, it would be that. If you do inequality notation, it would be that, from 0 to 5. Have y'all seen in either one of these? Both? Maybe? Okay. So that's the domain in the context. Now if we stripped away the context and just said, here's the graph of this quadratic, what's the domain? It would be from negative infinity all the way to positive infinity. Right? This graph is going to continue down and out this way. So every x value has one y value associated to it. So that means that the domain will be from negative infinity to infinity, or all real numbers is what we call that. But because we have the situation, the context, then we can think about the domain there. So that's how the context can affect the domain. All right. Any questions on either the key features, the domain, anything that we've gone over so far today? Okay. So hopefully we're able to reach our goal for this lesson, which was to understand how to multiply two functions graphically. And we're multiplying the y values at each x. We identify key features of quadratic functions, so y-intercepts, x-intercepts, vertex, axis of symmetry, those sorts of things. And then describe the domain of a function in context, which we did in that swimming problem. So hopefully we're able to reach our goal for today. So that's it for this video. In our next video, we'll expand more on quadratic functions and graphing them from 3 different forms: factored form, standard form, and vertex form. So I hope you'll join us then.